This video will go through two examples of how to use trigonometry with three-dimensional problems. As always, please take notes on the two examples. This first example is an easy one involving a rectangular prism. The second example will be a more complicated application problem involving a tower and looking west and looking south, but I wanted to make it clear, I hope to make it clear, that we can equate those word problems to a rectangular box just like this one. First, let's go through this one. Part A asks me to find the length of AC, which would be the diagonal across the bottom of this box. Now, if you're using a 2D brain, then it doesn't look like this is a 90-degree angle here, angle DAB, but we know, because this is a box, that in fact all of these angles that we see are 90 degrees. So while this looks like an acute angle, it is in fact a right angle. It's the bottom corner of a box. Angle ADS is also a right angle, and so on and so forth. I've now drawn in several right angles just to show you what we're dealing with. So again, I'm asked to find AC, which is the diagonal, or I should say the hypotenuse, of this right triangle along the base with legs of 5 and 12. If you know your Pythagorean triples, the hypotenuse here is going to turn out to be 13, but I could use the Pythagorean theorem and do 5 squared plus 12 squared, and that would give me AC squared. So here's my work for AC squared. 25 plus 144 is 169, and that's AC squared. And when I take the square root, AC turns out to be 13, and don't forget our units of centimeters. So that's the first one, which wasn't so bad at all. Next, we're asked to find AR. AR is going from the bottom base up to the opposite corner at the top of the figure. So now I want to look at right triangle ACR, which I'll draw in now. So I've drawn ACR here in the 3D box, but then I've also recreated the triangle here in a 2D format. I have no idea why there are these dark shadows now around this triangle, but hopefully you can still see everything okay. If you remember, we just found that AC was 13 centimeters, so I'm going to fill that in now. And now it's quite easy, hopefully, to find AR. Again, I'm just working with the Pythagorean theorem. 4 squared plus 13 squared will give me AR squared. So doing that math, AR squared turns out to be 185, and the square root of 185 is 13.601 centimeters. Finally, I'm asked to find the angle between AC and AR. If we use the figure that I recreated over here, the angle between AC and AR would be this acute angle down here. Since I know the side opposite the angle that I want and the side adjacent to the angle that I want, I should use the tan function. Because I'm looking for an angle, I'm going to use inverse tan. And the tan inverse of 4/13 is 17.103 degrees. 17.1 degrees is fine. Let's now look at our second example, which will be a word problem. But I'm going to refer to this box again to try and help us to understand an application type problem. Okay, so here's the same box, and we're going to disregard these lengths here. We're going to pretend that RC is a tower. Okay, so RC is a tower that's coming up from the ground, of course, and so the ground would be CDAB. That's along the ground. And if I'm at the base of the tower, I could walk due west and then look up at the tower, okay, and that definitely forms a right angle. Hopefully we can see that. RCD is a right angle. And I could use my angle of elevation, those type problems that we've done, and I could look up from angle D to angle R, and I would have an acute angle here and a right angle, and I could use my right triangle trig. What's a little more complicated to visualize is, again, RC is that tower. I could walk due south. So remember, this is a right angle here. BCR is a right angle. And so if this is due west, and this is also a right angle, then due south is CB. Now, if you're using your 2D brain, it doesn't look like CB is going south. It looks like it's going off southwest. But please keep in mind that this is a right angle. So you have to think 3D. If I were to turn this box so that this was facing me, this would definitely be a right angle. So this is walking due west, and this is walking due south. That's important for the next problem. Similarly, if I now say SD is a tower, then again, I could walk due south or due east. And if I say PA is a tower, I could walk due north. So from A to D would be me walking due north and then due east. Hopefully that helps clear things up. Let's look at an example. Okay, in this problem, PO represents our tower, and it's telling me down here that A is due west of O and B is due south of O. We have a right triangle, which is being pointed out here. AOB is a right triangle, which means that this is the hypotenuse. Now again, with your 2D brain, it does not look like this is the longest side of this triangle that's on the ground, but it is because it's across from the largest angle. So please, you have to keep shifting between your 2D brain and your 3D brain. Okay, so in our box over here, CD was similar to OA, and CB was similar to OB, and our tower was CR is now OP. And it's labeling the height of this tower as H. Okay, so in this question, we're asked to find the value of H. And it might look like at first glance we don't have nearly enough information because I do have two angles, but they're in different triangles, and I have one length, but it's in a third triangle. So at first glance, you might think, how possibly can we do this? What we need to do is come up with a system of equations to relate these three different triangles. So first, I'm going to work with triangle AOP. And I definitely want to involve the height because that's what I'm looking for, so I want to include that. And then I want to include this angle, and I also want to include side AO because I have that side is connected to this bottom triangle along the ground where I know a piece of information. So I'm going to set up my trig function involving the side opposite and the side adjacent, my 25-degree angle, which will be tan. So here's my first trig equation. I've rearranged it to isolate that AO is equal to H over the tan of 25 degrees. Next, I'm going to use this second triangle, POB, which I've redrawn down here so that it's easy for us to see that again I'm going to want to use this 33-degree angle. Obviously I'm looking for the height, and so I want to use H, and BO is the other side that's connected to the triangle involving 60 meters. So I want to use the trig function involving opposite and adjacent again, which is tan. So I now have two different equations, both of which involve H. However, overall, in my two different equations, I have three variables, AO, BO, and H. So when I have three variables, I need three different equations in order to solve that system. So I need another equation that relates AO and BO. Well, if we look at our figure, AO and BO are both legs of the right triangle that's on the ground with 60 meters as the hypotenuse. So I'm going to use the Pythagorean theorem to make an equation involving AO, BO, and 60 meters. So here's my equation involving the Pythagorean theorem. I'm now going to do some substitutions because I still have two variables in this equation. However, remember I'm looking for H. So I'm going to replace AO with the equation that I came up with up here. AO is equal to H over the tan of 25. So I'm going to replace AO with H over the tan of 25. Similarly, BO is equal to H over the tan of 33 degrees. So I'm going to replace BO with h of tan over tan of 33 degrees. So here I've done the substitution. Now this is not a pretty equation, but it is an equation that only has one variable. So I now can absolutely solve for h. I need to do a little bit of work first. So if you remember, in front of h is actually the coefficient 1. So it's 1 times h divided by the tan of 25 degrees. I want to do on my calculator 1 divided by the tan of 25 degrees, and then I want to square that number. So 1 divided by the tan of 25 degrees is going to give me some coefficient in front of h, and then I'm going to square that. I'm going to do exactly the same thing over here. You should try this on your calculator and pause the video, and hopefully we come up with the same answers. So here's what I got when I simplified above. Please keep in mind that even though I've rounded here, I've kept the full answers on my calculator, and I'm not actually going to round until the very final answer. So now that I have like terms here, 4.59 h squared plus 2.371 h squared, I'm going to combine like terms, which gives me 6.97 h squared, still equal to 3,600. I'll now divide both sides by 6.97, but please keep in mind that on my calculator, I'm dividing 3,600 by this full answer, not just 6.97. So now I have what h squared is equal to, and finally I'll take the square root of both sides to get that h is 22.73 meters. So that's obviously a long problem, and it took some good visualization skills, some good algebra skills, but in the end we were able to solve for h. I hope this video was helpful. Please feel free to watch it again, and we'll do some more examples together next week.